And so if all the spin-dependent information is then just in the difference between these two signals, and it looks like this. So you see at low temperatures we get a spin signal of like 6 milliohms, and at room temperature we still get 1 milliohm. So many of the things that we do, we can also do at high temperatures. You don't necessarily need to low temperatures. But one of the things that struck our interest was what's happening here. At very low temperatures, it looked like the signal is non-monotonic. There's a little bump. And again, if you look at this formula, that seems kind of surprising because, well, we know what the resistance does, right? It goes down, it goes flat. So this term does not give you this non-monotonic behavior. So it's either the spin diffusion length or the polarization. I mean, these are just geometric factors, they shouldn't change. And so how do we figure this out? Well, we can do this by so-called handler measurements. How does that work? Now we have the same device, but we apply the field perpendicular to the device, okay? And what that means is when you inject an electron, it will start precessing around the magnetic field. And therefore, this magnetic field will modulate the spin polarization that you measure at the second contact. And if you just assume that the electrons move ballistically from this end to that end, then the voltage that you should measure should just oscillate as a function of field. It should go up and down. Now, and if we switch the magnetization to be antiparallel, this oscillation should be just phase shifted by half a wavelength. But now, the transport is not ballistic. It means that each electron takes a different amount of time to go to from one contact to the other. And the spin can relax, it can flip. So what happens is that there's spin dephasing, and these signals are actually damped out. So instead of seeing something like this, you see oscillations that become smaller the bigger the field becomes. But you can take this data, and this is actual data taken on aluminum by Sergio Valenzuela and Michael Tinkham about 5 years ago. And you can take these oscillations, you can fit it to something that looks like this. Looks complicated, but it really isn't. And from this you get the injection polarization and the spin lifetime. And so we can measure this in our devices. Let me just go a little bit further. Well, this is the data that we see. And if this is for parallel magnetization, we get these oscillations. For negative, we get them like this. It looks slightly different for some technical reasons, but if you go just in the center and we fit it, ignore what's written up there, we can fit the data very well to this equation, and we get the spin polarization, the spin lifetime,